So hello, welcome. Today we're going to start chapter 8. Chapter 7 was the beginning of rotational physics. And it was, hey, remember kinematics? Let's do it, spinning. And chapter 8 is, we also did torque and energy and momentum. Let's make that shit spin too. And that's really what chapter 8 is. We're going to do everything we covered in chapters 4, 5, and 6 and set it spinning, literally. Um, that's the plan. Now, before I get into that, a quick other aside. Your second exam is upcoming. Exam 2 is on Friday, April 9th. That is 1 week from Friday. It'll be the same setup as last time. It's going to be at 2 o'clock. You have until 3:05 to upload it. It's 4 problems long. The problems will consist of the first problem will be conservation of energy. The second problem will be conservation of momentum, and the third and fourth problem will be rotational physics. That's going to mean chapter 7 and 8 mixed in. And I'm not going to lie, chapter 8 often shows up in problem 1 also, but I'll come back to that. But that is going to be the breakdown. It will go online at noon. Wait, noon? No, not noon. We'll go online at 2 and must be uploaded by 3:05. I will be on Zoom during the exam, just like last time. I have posted last semester's exam. I'm going to post solutions on Monday of next week after I cover it in class. Wednesday of next week will be a bonus review session. I'll talk about that later on as we get closer. And yeah, that's kind of all of that shit. So any questions about this exam before I continue? Cool. Let's get into it. And what we're going to talk about today is, or what we're going to start with today, we'll talk about a few things today, is torque. Let's say you want to make something rotate, and you're going to make something rotate around a fixed axis. And I have a video that shows this, but I also just have this thing here. So this guy can freely rotate. If I want to make it rotate, I can make it rotate one way or rotate the other. But there's 3 things that I'm going to have to think about when I want to make it rotate. One is how hard I push on it. Then if I just kind of go tap, it'll rotate a little slowly. If I go like and smack it hard, it can rotate quicker. That how hard I push on this thing will be how it rotates. And so when we're in person, I'd always do this versus a door. Like I walk around to the door of the room and play with it. But let's say you were trying to open a door, right? You normally open the door the far side from the hinges. You don't push right next to the hinges, but fall out. See, when you want to make something rotate, it's not also how hard you push it, but where. If I hit this right here, it'll rotate pretty freely. But if I hit it all the way down here, it doesn't rotate nearly as well. You see, when you're going to make something rotate, you have to think about where you push it. How far from the principal axis, or how far from the pivot point. That way it's pivoting around here. So if I want to make this move easily, I'm going to push it all the way out here and not in here. And the last is the angle. If I want to make this rotate and I take this and push, ow, that got me right, the back end of this right between the fingers. If I take this and pull it right along the length, aka if I put it like this way, straight along the length and pull it out, it's not going to start rotating. It'll rotate if I push it down or if I push up, but not if I push left or right. It won't rotate at all. And this gets into when you want something to rotate, you need to think about all of these quantities. How hard you push, where you push, and the angle at which you push. And this gets into the idea of torque. Torque, which is represented by the Greek symbol tau. It is not a T, it's a tau. Is the ability of a force to rotate an object around an axis. That, I think this is literally the exact same thing. It is. So not useful. And it is how easily, how much effort, how much you can succeed at rotating on an object. This is basically the rotational version of force. Forces is how you have to do to give an acceleration. Torque is going to be how to give something an angular acceleration. We'll come back to that idea. Well, once again, tau is torque, which is measured in a Newton meter. Now, for the record, a Newton meter is the same as a joule officially, but no one ever says joules. It's in Newton meters. F will be the force. R will be how far from the pivot point you apply the force. And theta is the angle between R and F. Now, traditionally, we like to always measure our angle from the horizontal. That is not the case in torque. Torque is the angle from, actually, no, I'm going to use the video for this so I can draw on it. Theta is the angle between R and F. Right now, with my right hand, I'm pushing down that way. This would be the direction of R. R would be the distance from the pivot point to where the force is applied. And so this would be at 90 degrees. But if I looked at if I instead, let me find a different spot in the video. That's probably would work. Right here, I'm hitting this thing like that way. R is this way. That's still 90 degrees. It's not the angle from the horizontal. It's not the angle from the vertical. It's the angle between R and F. It is this angle. The theta is always the angle between R and F. Okay. Now, of note, if R and F are parallel, you don't apply any torque, which makes sense. Going back to this guy, that if I just push on this thing straight on, it's not going to spin. It's only when I move it at some angle, up or down, that I cause it to spin. Anytime R and F are parallel, there is no torque. It's only when the force is at some angle relative between R and F that you can have a torque. Now, some of you might be familiar with the idea that if you're struggling with like a bolt, the answer is often just get a bigger wrench. And here's the problem. I'm going to solve like one. But let's say you got a bolt you want to open and you can't get it. And so you get a bigger wrench and you can loosen it. The reason why, and I pose a question, but I'm not going to do it that way for online, is that you apply more torque. Right here, what I did is I attached a bolt to this thing and I tightened it super hard with this little wrench. I can't loosen it. If I take that same wrench and put this huge ass pipe on the end and push all the way at the end of the pipe, I'm pushing at a bigger radius. Suddenly, and it's hard to tell in the video, so I apologize, but suddenly I'm able to loosen this bolt. I can loosen it because I increase the radius. Oops. I increase the radius. And because I increase the radius, I apply more torque. So yeah, you can't get something to spin. Don't necessarily push harder. You can, but push smarter. Go out to a much bigger radius and you apply more torque. More torque, the more likely it is to make something move. Basically, this video is, let me pause that. This video is right here. That I had the small wrench versus the wrench with the pipe. If I make the radius twice as big, I apply twice as much torque. Make sense? Now, in forces, we always talked about net force, right? That it never mattered what a force acting on something, it was the sum of the forces. Well, net torque is going to be the same kind of idea. But for net torque, we're not going to talk about up and down. Because let's think about this. If I push down here, it spins one way. If I hit down there, it spins the other way. If I push down on both sides, it doesn't spin at all. My torques are canceling each other out. Even though both forces are down, my torques still cancel. And if I was to push up here or push to the left here, or this is probably to your right because I think it gets mirrored. So to the right for you, up at the top. So push this way and this way. They also add up. Well, if I was to push down here and this way here, they'd cancel each other out. So I can't use the directions of normal forces. The general idea is we will say any torque that causes counterclockwise movement is positive. And so if I push, oh, this is going to really mess with me because everything's reversed. Push down here, that's here. So if I push it like this and it starts moving counterclockwise, that means pushing down here causes a positive torque. Anything that causes a clockwise movement will be a negative torque. That is how we're going to define it. And we'll only have one dimension for torque. We don't have to deal with like two dimensions like we did with forces. But it will just be a positive torque or a negative torque. A positive torque being counterclockwise, and negative torque being counterclockwise. The reason Y is officially torque is along the Z-axis, and it's doing something called the right-hand rule, where you curl your fingers in the direction of the movement, and your thumb points at the direction of the torque. And really, in a standard coordinate system, Z would be out of the page. And so if it goes one way, if it goes this way, that's a positive Z, positive torque. If it goes this way, that's a negative Z, negative torque. That gets into some calc shit and cross products, so I'm not going to do more detail there, but that's the general idea. Any questions? So an example problem. Let's say we got two people. One of them is really stupid, but both of them want to go through a revolving door. And person one is pushing the door one way, and person two is pushing the door at the other because apparently they've never seen how a revolving door works before. Let's say person one is pushing with 625 newtons at a distance 1.2 meters from the center. Person two is pushing with 850 newtons. They're pushing a hell of a lot harder, but they're only 0.8 meters from the center. Which way would the door swing? See, what I can do is I can say the net torque in this situation. That the net torque, which is always going to be important, it's not going to be what one torque is. You can only want the net torque. The net torque will be just the torque of one person plus the torque from another. And torque is all F sine theta. And so the torque of person one will be the distance R1 times the value F1 times the sine of the angle between them. But let's look at this picture. The angle in this picture is 90 degrees. And the sine of 90 is 1. Anytime your force and radius are perpendicular, you can get rid of that term. Then I can go and figure out the sines. See, torque 1. If torque 1 was left
I got
to
a
its
question.
Yep.
Why are we finding the sum? I thought we were just trying to find which one is greater.
That's what I'm going to do. I'm going to add them up, and whatever one's greater will be the direction it goes in.
Oh, okay.
I could have done it like that too. Yeah, that works.
Okay.
I'll be dealing with sums in a bit more too, moving forward. You'll see why. My pen disappeared. Let's try that again. So person one, nope, not that. This. If they push up, they're going to make it spin this way. Spinning that way, that's a clockwise direction. And so person one is going to be a negative torque. If person two pushes, they're going to push and it's going to spin this way. That's counterclockwise. So person two will be a positive torque. And therefore the net torque will be negative R1 F1 plus R2 F2. Where I can plug in my values and get a negative value. The fact that my final is a negative value, that means it's going to go clockwise. That means person one, who's the one going through a revolving door in the correct way, is the one who's going to win out. While person two, who's going in the wrong way, pushed a hell of a lot harder, but it doesn't matter. They didn't push as far out. They had a smaller radius. Any questions though? That's not what I wanted. I wanted this. I forget what the next video is. Okay. Any questions? Now, this net torque idea is going to get into something that we have glossed over like crazy so far. You see, way back when in chapter 4, I said something that wasn't necessarily 100% true. I lied to you for my own benefit. Oh, let me put this guy back into place. So, remember equilibrium? We talked about equilibrium in chapter 4. And we said for equilibrium that something is in equilibrium when the sum of its forces are equal to 0. That if I push something one way with a force and something else the opposite way with the same force, if they cancel out, it doesn't move. Right? Actually, let's do up and down instead. So if I push this down and push this up and the magnitude of the force is the same, it won't move. But what if I do this and apply the same forces out here and here? If I apply the same force out here and apply these forces, it's going to start spinning, right? If I push down here and up here, boo, there we go. And that doesn't seem equilibrium. Equilibrium means that if something's stationary, it stays stationary. If something's moving, it stays moving the same velocity. If this suddenly starts spinning when it wasn't before, it goes from not spinning to spinning, that means some shit changed. So that's not equilibrium. You see, earlier when I said equilibrium means the sum of forces equals 0, that was not the full story. That was only part of equilibrium. You see, there's another part of equilibrium. Equilibrium is when the sum of forces equals 0, but also when the sum of torques equals 0. To be in equilibrium, both must be true. This is sometimes referred to as translational equilibrium and rotational equilibrium, but true equilibrium needs both. To be in equilibrium, your sum of forces must be 0 and your sum of torques equals 0. No, this actually means 3 equations because it'll be the sum of forces in x, the sum of forces in y, and the sum of torques. Any questions there? Okay, I'm about to do a problem. But before I do a problem, I keep changing the order I put these notes in. I haven't yet really decided how I should do this, like the order of this next bit, because I kind of want to stick to talk before I jump to another topic, but I kind of need to jump to another topic to explain us something. So I'm going to kind of talk about a topic a little bit and then go into detail later on. And that's something called center of mass. We're going to talk about center of mass a lot later today, but I'm just going to say, if you have a complex, let's say you got this beam, right? And you want to do forces and torques on it. If you have a large object, when you talk about torques, you have to say not only what the force is, but where the force is. If you have something like a long plank, it has mass here and here and here and here and here and here and here all the way down. And I could say that everywhere on this thing, there is some force pushing down throughout the entire thing. But if you have a long object and it's uniform, like a plank, we're about to do 2 problems with planks, you can just say that it's as if the whole thing was weightless, except for one point in the direct center, that all of the weight is in the center. It's an approximation, but it works very well. And so anytime you have something like a plank, say all of its weight happens at the center of it. Does that make sense? As I said, I'll do more detail that later on and what happens when you have complicated shapes. So using the sum of torques equilibrium problem, let's actually solve a problem, that fact. And this is taken from a textbook, but let's say I got a woman of mass 55 kilograms sitting on the left end of a seesaw at distance 2 meters from the center. And the seesaw itself is 4 meters long and has a mass of 12 kilograms. You know what? We'll go Funko Pop. So woman, man. So what we say is a woman sits on one end of the seesaw. A man who is 75 kilograms sits somewhere else. And he sits at a place. We're good. He sits at a place so that the weight is balanced from a pivot point right in the center. That if I put a pivot point, stay, right here, I give up, I'm just giving up. This isn't working. The whole thing is balanced and stays perfectly balanced. My question is, oh, her head is loose now. I never think to pull things out like this ahead of time. You know what? Big ol' base. Got it. Haha, Solido. So my question is, wow, these are dusty as hell. Is that if it's pivoting just on that point, how far away does this guy need to be from the pivot point to perfectly balance? Okay? If we're going to do this, if it's perfectly balanced, if it's not moving, that's going to be equilibrium. Oh, and I also say, what's the normal force? Well, I'm asking for the normal force, aka if this is just being held up by some point here of the thing it's sitting on. If this is an equilibrium, if this isn't moving, I can say that the sum of forces must be zero, but the sum of torques must also be zero. That is what equilibrium means. And so I'm just going to set those both equal to zero. And if I'm going to do forces, well, we start all force problems the same way. How we start force problems is we say we make a free body diagram. And how we're going to start force torque problems is going to be the same. We're going to start with a free body diagram and say where the forces are. But as opposed to forces where I just drop wherever, I have to mark where they are. See, I can say on this beam, the force is acting here if it's just sitting on a piece. I can say is the woman has some mass, so she has a force. She's on the very end of the beam, so I'm going to put her force right on the end. The man has some weight. He's at some point, woo, just launch that weapon. He's at a point X where we don't know where X is. This is so dusty. So we're going to have to go and solve for it. But there's also the plank itself. The plank itself has weight. And because the long plank, I'm going to assume all of its weight is at the center. And right at the center, it's held up by a normal force. Any questions here? I'm going to stop playing with my toys now.
If we're just trying to find how far out he's sitting, do we have to take in the weight of the board?
Not for that, you won't need to, and we'll show exactly why in a second. But I did say, how far out is he in? Is he? And I said, well, so what is the normal force? So we're going to need it for that.
Okay.
So let's say I do sum of forces equals zero. If I do sum of forces equals zero, I can say forces up minus forces down equals zero. So up, I have N, and down I got her mass, his mass, the plank's mass. Or weight, I should say. His weight, her weight, the plank's weight. So M1G, M2G, and M plank G. Now, if I try to solve this isn't going to help me with X at all. But I also know the sum of torques equals zero. And for the sum of torques equals zero, each torque is RF sine theta. Now let's look at our angles. Every single one of these is at 90 degrees because all is flat left and right. And the forces are straight up or straight down. So those cancel out. So I'll just say in this case, torque is RF. And I'll write an equation for each one. I'll say the sum of torques. Let's go left or right. Well, my first one is M1G. M1G is 2 meters away. If left to its own devices, this is down and that way. This is going to spin counterclockwise, so it's positive. The man's mass is a distance x away, and so it's m2gx. But left to its own devices, this is going to go this way. That's clockwise, so it's negative. But the plank is at the pivot point, and the normal is at the pivot point. What that means, the value for all for the plank and the normal is zero. And if the value of all is zero, the torque is zero. This is going to be a common thing when doing these problems. When doing these problems, you're often going to set forces at, you can sometimes change where the pivot point is going to be. I'll come back to that idea in a while. And if it's an equilibrium, you can make really the pivot point wherever the hell you want. Once again, I'll come back to that. But If any forces at the pivot point, give no torque. That the forces right where this pivots around are not going to cause it to spin at all, because they're not causing spin, they're just at that spot, and they won't apply anything. And so the sum of torques would just be m1g_all minus m2gx. I can add m2gx to both sides, divide both sides by g, and divide both sides by m2. And this will let me solve for exactly where he needs to sit. Now, if I do want to solve for the normal force, my sum of torques equation isn't going to help me. I can't use the sum of torques equation to get the normal force. Normal force isn't in it. But I could go back to my sum of force equation and rearrange and solve for the normal force. Questions? This was kind of a simple one. I'm going to do a slightly more complicated in a second. Okay. This one is a little more like the ones you can see on the homework. A uniform plank of length 2 meters and mass 30 kilograms is supported by 3 ropes, as indicated by the blue vectors. Find the tension in each rope when a 70-kilogram person is 0.5 meters from the left end. I'm looking for 3 unknowns. If T1, T2, T3. If you want 3 unknowns, you need 3 equations. Whenever you're solving for a problem, you need as many equations as you have unknowns. And like always, I'm looking for something. It doesn't actually say forces. It doesn't say equilibrium, but you're solving for a tension. A tension is a force. And if I'm solving for a tension, I need to start with my free body diagram. Now, the free body diagram is partially done. T1, T2, T3. But I have to say what other forces are acting on the plank. And so, what forces are acting on the plank? I'm going to ask you guys.
Gravity.
Gravity is acting on the plank. What else is acting on the plank?
Tension with nothing else. Right?
Tensions are there. There's one other one. There's someone standing on it. And if someone's standing on it, they're pushing down on it.
Oh.
And so, yep, there'll be 2 other forces. The mass of the man, G, damn the man, and the mass of the plank, G. Now, the mass of the man, G, that force is going to happen where the man is. The force of the plank is going to happen at its center of mass, at its direct center. And if I write down the values that was given, the length, the mass of the man, the mass of the plank, his distance, I can try to solve these things. Oh, I'm about to sneeze. Those figurines I took down, I was so goddamn dusty. So let's look at solving this. If this is not moving, I know equilibrium. Equilibrium means the sum of forces is 0. But that's really 2 equations. The sum of forces in x equals 0. The sum of forces in y equals 0. Now, I do need to be careful that my T1 will need to be broken into components. That there really should be a T1x, which is going to be T1 cosine of 40 degrees, and a T1y, T1 sine of 40 degrees. And I can say an x is right minus left. So T1 cosine theta minus T3 equals 0. In y I can do up minus down. Up I got T2 and T1 sine theta, and down I got both mg's. So it'll be T2 plus T1 sine theta minus mg equals 0. Now both of these equations are kind of annoying because I want to solve for T1, T2, T3. My first equation has T1 and T3 in it. My second equation has T1 and T2 in it. I have 2 equations, 3 unknowns. This is not going to be solvable. But what I can do is say sum of forces 0 is not my only equation. If I'm in equilibrium, the sum of torques must also be 0. Well, each torque is all F sine theta. And what I can do is I define my pivot point. See, let's think about this. If T1 disappeared, this whole thing will go whoop like so. if T2 and T3 disappeared, this whole thing would go whoop, like so. There's no set spot this is pivoting around. I could say it's pivoting around this side, or I could say it's pivoting around this side, or I could say somehow magically it's pivoting around the dude or the center of it. In equilibrium, you can make the pivot point wherever you want. But keep in mind, wherever your pivot point is, always going to be zero there. And so if you make your pivot point selectively pick that spot, you can simplify equations. I could eventually solve this problem putting my pivot point in any given spot, but the easiest way to solve this problem is say my pivot point is the left end. I'm going to say this right here, that blue dot I just drew, here's a big old blue dot, that's my pivot point. If that point is my pivot point, I can then solve for the sum of torques around it. But I can say at that point, the torque from T2 is 0 because that's the pivot point. At that point, my torque from T3 is 0 because that's the pivot point. My torque from the man is going to be mg for the man times d, because that's how far away he is, sine of the angle, and it's going to be negative because that's pulling clockwise. The torque from the plank will be mg times a half of L, because that's the halfway point, right? If the whole thing has a length L, halfway is going to be half L. And it's also going to be negative because that's also going clockwise. And T1 is at the end, has a value T1, and is at the sine of theta, and at an angle theta. Anyone stuck where I got all those? Now, the sine of 90 is 1. So every side of 90, I can say equals 1. This has only one unknown. I can solve this for T1 because everything else is known in here. I know M, I know G, I know D, I know L. I know theta. And so I'll take this equation and I'll say, okay, let's solve it. I'm going to take both mg sections and add them to both sides. I'll then divide both sides by L sine theta. And at this point, just plug in numbers. Get a value. Questions? I mean, that problem's not done. That's T1. I asked for T2 and T3. And I could, to solve for T2 and T3, I could make torque around a different point, but that's just a pain in the ass. There's going to be a bunch of problems on the homework where I ask for multiple forces or multiple torques and something like this. Usually, use sum of torques to get the first one, and for the other ones, use your force equations. See, because what I can say is I now know T1. And if I look at my force equations, I got this guy T1 cosine theta minus T3 equals 0. That means T3 equals T1 cosine theta. Or, 572 cosine 40. For T2, I'll just take my y equation. And I'll move everything that isn't T2 to the other side. Plug in some values. There you go. Questions? Now, in doing this problem, I did make an assumption, and that was the center of mass of the plank was at the center. That I could claim all of the weight at the plank exists right in the center. This works because it's a uniform object. But that assumes, it's uniform. It's not changing. But if I take something that is not, here we go, as I pull from other action figures. If I take something that isn't uniform, that the shape is not the same everywhere, it's probably not going to be the center is going to be in the middle. It's probably going to be off on one side. This is not well balanced. To account for the fact that one side is not the same as the other. And so if you do not have a uniform object, you're doing the sum of torques on something, you might need to solve for where to treat the center of the object if it's not going to be just the middle. This is called the center of the object. Where you put all the mass is called the center of mass. That if you have a complicated object, you can say the center of mass. Also, sometimes called the center of gravity. I think I call it center of mass everywhere, but whenever you center of gravity, it's the same thing. What that's saying is for any physics likes to do point masses. They like to say that all of the mass is at one spot. That this plank, all of its weight is right at the center. What it is when you have the center of mass of something or the center of gravity, that's just saying this can be like the whole thing weighs nothing and all of its weight is in one spot in the middle. It'll simplify it and make it less complicated. See, the general idea is if I want to find the center of this shape, which happens to be this white dot, trust me, it's been solved for. What I can say is that for this complicated shape, I can treat every infinitesimal spot of it as a little tiny mass with a weight m. And I can find its x and y location, like x comma y, how far over, how far up. And I can use that to define the mass. Now, for a solid object, you're going to need to take an area integral, which we're not doing. This isn't calc-based. But if instead of a solid object, if you just have a bunch of point masses, you can solve for where the center is by saying for an equation x, equation y, and say the center of gravity or the center of mass of x will be each point mass's mass times its position over the sum of the masses. And in y will be each point mass's mass times their position. Why is this? Sorry, this guy is like way far over. I don't know how that happened. Over the sum of their masses. If you just have two things, which would be m1 x1 plus m2 x2 over m1 plus m2, this will allow you to solve for the center of mass. That if you have a complicated shape, where is its center? Once again, though, this really only works if it's a solid thing. That's going to be complicated because you're going to have to say each infinitesimal space. If it's a series of point masses, though, it's pretty straightforward. Let's say I didn't say center of gravity here. Let's say I got this set up, and I said I have these three spheres: a 5 kilogram, a 2 kilogram, a 4 kilogram, in the locations printed. Where is the center of mass of this system, or where is the center of gravity of this system? You see, it's not just going to be right in the middle because they have different masses. And if I label these 1, 2, 3, I can find the center of mass in x and y. Now I'm only going to do x here because nothing's happening in y. I'm going to ignore y entirely. But I'll say for x, the center of mass in x is the sum of xm over the sum of m. I have three things. That means it's going to be x1 m1 plus x2 m2 plus x3 m3 over m1 plus m2 plus m3. And I'll just go and solve. I'll say for number 1 is a distance 0.5 centimeters to the left of my 0. So its position is negative 0.5 meters. And its mass is 5 kilograms. For 2, it's at my 0. So x is 0. M is 2 kilograms. And 3, x is 1 meter. M is 4 kilograms. And I'll divide that by the total. Now this term in here is 0, because 0 times something is 0. And 5 times negative 0.5 is negative 2.5. 4 times 1 is 4. And I can get a value. That's where the center of mass is. Okay. Now, why did I suddenly talk about the center of mass thing? Why is this important? Simple version. Let's say I was to take this guy and throw him up in the air spinning, right? So there he is. Take him in the air, throw it in the air spinning. When I do this, if I try to plot like this piece right here, what I get is it kind of goes, you get a weird shape. But when I throw this, watch the white dot. The white dot makes a perfect parabolic motion. In a complicated object, if you treat it as a point mass with everything at its center of mass, it'll follow the laws of physics. That if you throw a hammer, if you try to plot the head of the hammer, I get this shape that, I mean, it's almost a parabola, but it's not really. It's off a bit. Even worse, if I tried to look at the other end of the hammer, I get this shape. That's some complicated physics right there. But if I plot the center of mass of the hammer, I get a perfect parabola. That throwing a hammer like that is going to bypass all the laws of physics we covered in chapter 3 for projectile motion. That you can take any complicated shape and treat it as a point mass if you work in the center of mass. Okay? Okay. Now, before I can go further on torques, I need to do a quick aside. Another aside. I guess center of mass was already one. So let's talk about something else real fast. In F equals ma, we said mass was the ability to resist accelerations, right? And we said that mass was really inertia. Mass is how we measure inertia. The ability to resist accelerations. There is also rotational inertia. See, inertia is just to resist acceleration, but rotational inertia is the ability to resist spinning. And straight up inertia, yeah, I do the video instead, is going to be, yeah, how much is weight, how much force do I have to do to hit it? Rotational inertia is just how hard you have to work to make it spin. And rotational inertia, though, for some reason isn't called that. Rotational inertia is the logical name, but it's normally called the moment of inertia. And the moment of inertia is something is how hard to make it spin. See, if I take this and just kind of smack it right now, spins pretty freely. If I instead take all of these weights and move them to the edges, if I smack it the same amount of hardness, it barely spins and I actually hurt my hand a little bit. I didn't change the mass of the system. I just moved the masses to the edges. But when the masses were in the middle, it spun much more freely. That's because I'm changing the moment of inertia. Well, moment of inertia is ability to rotate. See, very fast. What we can say is if you have a tangential force, if the angle is 90 degrees, torque is RF sine theta. So if the force is tangential, it's just going to be RF. If you apply a torque on something, you can say F equals ma, so we can say that force would be ma, where a will be tangential acceleration. Remembering the fact that tangential acceleration is R times alpha. You see, forces cause accelerations. Torques cause angular accelerations, or rotational acceleration. And what I get is this other term. That mr squared is what we're going to call the moment of inertia. The moment of inertia, which has units of kilogram meter squared, is an equation for a set shape. That's going to be how well it resists spinning. And I think this is just going to be the exact same thing I just did. Yep, that's the exact same thing I just did. And it's just going to say how easily something can spin. Now, for a particle, for a point mass, we can say the moment of inertia is mr squared. Well, m will be how much it weighs, and r is its distance from the pivot point. For example, if I just take this guy and start spinning it around its fabric, I can say the moment of inertia this guy is spinning is the mass here times this distance squared, because it's basically just a solid mass at the end of a rope, and this weighs basically nothing. If you swing a mass m at the end of a rope, I is mr squared. If you're swinging something more complicated, if I'm spinning this, where the mass is everywhere, or that other guy I was spinning, or maybe I'm causing a football, ooh, that's a good one, to spin, right? There is a more complicated equation. I don't expect you to know your moment of inertia equations. I will always give them every time they're needed. But the moment of inertia of any shape spun would depend on the shape of it and where you're spinning. A thin rod around the middle is 1/12 ml squared. A thin rod around the end is 1/3 ml squared. A solid disc is 1/2 ml squared. A thin hoop, which I don't have a thin hoop right here. A thin hoop is ml squared. A solid sphere is 2/5 ml squared. A spherical shell is 2/3 ml squared. There's a lot of other things. As I said, I'll give them these to you as you're needed. But this will be their rotational inertia or their moment of inertia. Once again, moment of inertia is the normal phrase. And this will say how hard it is to make something spin. Where it'll be the mass and not just how much mass, but where it is. Actually, no, we'll just go to the video. That's why that I can spin this thing really easy when these masses are at the end, it spins kind of slow. But if I put these masses into the middle, it spins faster because I'm changing the moment of inertia. It's not just where the forces are, or not just what the forces, it's not just what the masses are, it is where the masses are. And what we're going to do with this is we know in one dimensional, the sum of forces equals ma, that the sum of forces is mass times acceleration. Oops. That's what we know. Well, mass is inertia. And in equilibrium, the sum of forces is zero. In equilibrium, the sum of torques is zero. But not in equilibrium, the sum of forces is inertia times acceleration. And what we're going to say when you apply torques is you give an angular acceleration. And what it is the sum of torques will be I alpha. That anytime you set something spinning, if you know it's inertia, you can figure out how fast it's going to rotate. You just add up all your torques and set it equal to I alpha. And you'll solve problems just like in chapter 4 in forces, where you'll make a free body diagram. You'll solve where the forces, look where the forces are. Solve for where the torques are and go through. $3 minutes? Yeah, I think I can do this. We good for me to do a problem? Okay. Let's say I have a frictionless pulley. It's the same as a 0.8 kilogram solid cylinder. It has a raise of 0.3 meters. And there's a rope going over it, as shown in the figure. So you don't see the rope, you see the arrows. And the rope is pulling on it on both sides. 10 newtons going one way, 12 newtons going the other. What's the angular acceleration? So I'll say this thing has a mass. It has a radius. And there's two forces, an F1 and an F2. What's the angular acceleration? Okay, good so far? What I know is the sum of torques equals I alpha. That means the torque from force 1 plus the torque from force 2 equals I alpha, where torque is all F sine theta. Here's the thing though, if you put a string over a pulley, it's always going to be 90 degrees. If I try to put this string here, it's going to pull directly 90 degrees from that. If I try to go to a different angle, it's just going to change the point of contact. This is basically what I got, something pulling either way like this. And so a string over a pulley will always be at 90 degrees. So I can say in this case, sine of 90 is 1, torque equals RF. Now, let's look at them. I said force 1 is the 12. Force 1, when left to its own devices, is going down, is going to go this way. That's counterclockwise. This guy is positive. Force 2, when left to its own devices, is down in this way. That's clockwise. So it's going to be negative. And so what I'll say is R1 F1 minus R2 F2 equals I alpha. Now, both forces are at the same radius, so I can factor that out. And if I want alpha, I'll just divide both sides by I. And I didn't necessarily say what I is, but I said it was a solid cylinder. Once again, I would give this on homework and stuff. But for here, I just say, hey, let's go 3 slides ago and look it up. The mole inertia of a solid cylinder is 1/2 mr squared. So that's my value of I, allowing me to cancel out an O. And dividing by 1/2 is the same as multiplying by 2. So I can plug in and solve. Okay? So that is everything we did in forces, again, rotational. We still have to revisit everything we did in chapters 5 and 6, energy and momentum. And that is what we're going to do in class Wednesday. We're going to look at everything from chapters 5 and 6, rotating. I'll leave you there, though. Have a good day. I'll see you then.